I guess I'll go first. I'm Daniel Cross from Cadence Design Systems. This work was motivated by a desire to create an example that would show people the utility of IEEE 2416 for system level power modeling. As such, we needed to create a system that looked more or less like a modern SoC that had lots of different kinds of components with different kinds of power models and at different levels of abstraction. The concept being that you put together a system model with what you have, and as you learn more information about how things work and how designs are coming together, you can refine your models, and your 2416 models can be refined along with them. We started with things we already had fairly detailed simulation models of, including a RISC-V based rocket chip, for which we had a System C instruction set simulator that was at least instruction level accurate, and an RF transceiver system for which we had real number models of the functional operation for receive and transmit, and a fairly detailed model of the PLL, which we'll see. And we also have functional models for clock and power management, including linear regulator models and the clock PLL that is reused from the transceiver. In addition, we used an AHV bus for which we had bit level HDL models. Then to make this look more like a system on a chip, we added a number of other modules in various stages of planning. We added a larger processor to do the actual hard calculation. For that, we used the Berkeley out-of-order machine, a neural network accelerator to help with inference, an image sensor model, and memories and the like. And what we were hoping to show is that you can use IEEE 2416 to model all these things in a single simulation using a common modeling language, a common framework for power, regardless of what design abstraction that you have to use, and all without the use of spreadsheets. While we think that IEEE 2416 is ideal for this purpose, the message I really would like to deliver is to please, whatever you do, stop using spreadsheets for your power planning. A key goal for our demonstration is that it should simulate very quickly. We want to encourage a verification strategy that uses high-level abstract models to run tens or hundreds of thousands of scenarios to make sure that you've covered your functional operating space, and to get power information out of those same simulations so that you don't have to do a separate analysis to look at power. Then, as more detailed simulation models become available, you can rerun a subset of those scenarios with the more detailed models, make sure that the assumptions you made in your abstract models are correct, and refine them if needed. And since your 2416 models will easily scale in detail and complexity along with your functional models, you can check your assumptions in power budgeting as well. So we wanted to make sure that our demonstration simulations had at least one realistic scenario for our system. And finally, we want to make the demonstration project available on favorable license terms so that people can try it out themselves, maybe even add their own IP blocks with their own 2416 models and continue to simulate. As such, although we used Excellium as the simulator to run the demo here, we tried to make it as simulator agnostic as possible. So here's the one sequence that we coded, trying to make it as realistic and as interesting as possible. We start in a power on reset state. The RISC-V rocket core boots up and does some system configuration, including setting the radio to transmit on a certain frequency, and then a receive of the requested data. And then the rocket core pre-processes that data, passes it off to the boom core, first requesting the clock PLL to spool up so that the boom core has a clock, and then the boom core does its thing, and finally the system goes back into standby. Since we have so many levels of abstraction, there's a lot of different inputs to the simulator. We have the RISC-V firmware that has to be compiled for the Spike instruction set simulator that's going to run under System C. We've got some plain old Verilog HDL for the AHB as well as the structural netlist. We have System Verilog real models for the transceiver and the power management and the PLL, and some System C test bench elements to manage the transaction level radio I/O as well as some other traffic. All of that is digested by the simulator. In this case, we're using Excellium. And the simulator produces some signal waveforms in the form of VCD files and a set of program counter and opcodes from the instruction set simulator. Those get pre-processed using the 2416 models to produce a scenario file, which is what PowerCalc uses for system level power modeling. And then PowerCalc uses that scenario file in conjunction with the IEEE 2416 models that have the actual power information in them to produce power estimates, including the graphs that we will look at. Here is another view of the simulation, showing through color coding what parts of it are test, what are actual hardware, what are mixed, what's in System C, what's in System Verilog, etc. Here are some details on the analog components and how we modeled them. First, the system power source is a nominal 4-volt input, which would be from, say, a lithium-ion battery. We have functional models for power reset, a voltage reference, and a 32 megahertz clock reference, which could be from a crystal oscillator. We've got a total of 5 load dropout voltage regulators that supply real valued supply nets, and we use these to show realistic power scenarios. When a block is not in use, we turn off its power supply by disabling the LDO. The receiver and the transmitter are modeled very simply using baseband models. We take an RF signal that's really a real valued plus or minus an amplitude that depends on the bit value, and we translate that to bits with a channel data rate of 1 megabit per second. The PLL is more detailed with separate models for the VCO, the phase detector, loop filter, and divider. And for the clock PLL, as I mentioned, we reuse the radio PLL. As I mentioned, the receiver model is fairly simple. One of the primary things we wanted to capture is the long warm-up time for the analog to digital converter reference voltages. So for our power model, we have 3 states, including standby, where the power is on, but everything else is disabled. That ADC warm-up time, which is before we've turned on the high power RF front end, and a full run state where everything's on. In addition, we have a couple of event-dependent energy consumptions, including the A to D converter when it takes a sample, and the mixer when it gets hit by an edge of its LO input. And then for state-based analysis, which is what PowerCalc is going to use depending on its scenario file input, we use eval mode and eval event to compile power numbers for those various states. And since for the PLL, we have more detailed functional models, we also have power models at a greater level of detail. Here's a snapshot of the power model for the VCO model and for the phase detector. And I mentioned we're sequencing the power by turning off supplies to blocks that aren't in use. In this waveform diagram, you can see that the PLL is on for receive and transmit, where the receive is only on for receive and the transmit power is only on for transmit. Since the simulation produces actual voltages on real valued power nets, we can use those voltages in the 2416 model using the new 2416 syntax. On the right here is a power trace generated for us by PowerCalc, broken out by the various LDO outputs, and we've labeled the various stages of power sequencing in the system. You can see, for example, that during radio transmit, there's minimal power in the LDO Dig1, which represents the RISC-V, but a lot of power in the radio transmit LDO. One thing to point out here is that we are using the RISC-V to sequence the radio, So there's a significant amount of RISC-V power during this interval where we're waiting for the ADC to warm up. We have to keep the RISC-V alive so that it can time that interval. So this points out the need in the system for some sort of state machine to manage the radio sequencing so that we can put the RISC-V into standby and save some power. Time has come to show you the actual simulation in operation. And I have a video I'm just going to let run real time so that you can see how fast this actually is. On the left, you can see our log file with AHB traffic and radio data going across the channel. And on the right, on the waveforms, you see at the top the AHB traffic. Below that, the various LDO voltages turning on and off. The signal is going across the RF channel. The simulation is done already, 1 millisecond of simulated time. And toward the end of the simulation, we activate the clock PLL in preparation for the boom core to do its thing. And we'll zoom in on that and take a look at the detailed functional waveforms we have for that PLL. Here is the VCO tuning line and its instantaneous frequency. And we can see the lock transient as our PLL comes to rest at the desired frequency. Zooming in even more, we see the waveforms for the divided VCO output and the reference frequency and the output of the phase detector providing signals that make the PLL lock. Next, we have a piece of video showing the process of pre-processing the VCD files and running the PowerCalc, narrated by Ali.
To show you the steps that we took to run UPM PowerCalc at system level and generate some static and dynamic results that is presented in this presentation. Here you're looking at the activity file or the VCD file of a simulation that was basically described how it was obtained. And then we have also a UPM model for the all the subsystems in this design. Here we're looking at the radio UPM model for the radio, and by using basically information in the UPM file where it describes each mode or each state, what are the conditions for each mode or each state basically, and by looking up the data, corresponding data of these parameters in the when conditions, we can determine each instance of each cell at what time instance they change state. And for example, in this model for the radio, we have states off, standby, warm up, ADC warm, and run. And so we determine this is the instance of radio at what instances changes from what state to what state using a script with the two pieces of information, which is UPM file and activity file, VCD file. By running this script, you basically come up with a collection of scenarios. Each line is a scenario statement, and in the scenario file, and I have highlighted the same radio here, which starts in state off and then moves to standby state, followed by warm-up state, and then run state, back to standby, and then finally to off. So this file basically has the collection of all the activities or scenarios that the entire system, each subsystem goes through. And once we have this description and the UPM file, we basically are at the point that we can run PowerCalc simulation, and PowerCalc goes through each scenario and finds basically the corresponding static and dynamic powers. Once this process finished after a minute or so, we basically, among other formats, we get a JSON format output that each at time instances and the instances of the subsystems that they have basically changed state, and the corresponding dynamic and static powers. And these states are going to stay in effect, or numbers are going to stay in effect until the state changes again. So once we have this data, we can do all sorts of analysis. And here I'm just doing some post processing to show the stacked plot for rocket tile, boom tile, CPMU, and radio, and other similar plots that you see in this presentation.
We're using the RISC-V rocket core in a system management role, and I want to emphasize that the system events that are occurring that are driving our power analysis are actually coming from C code written for the RISC-V. Here's a snippet of the code on the left. And for example, when the RISC-V code causes a write to address 2200, a value BD, we look on the waveform outputs and we see address traffic to 2200, a value BD. And in response, the RX VDD LDO turns on. In addition to that functional detail, the power model we have for the RISC-V is an energy per instruction model. And for details of that model, I'll turn it over to Rhett.